My name is Dr. Julian Seidel. I'm an Australian deep foundation specialist. My PhD was in drilled shafts, but my industry expertise is in driven piling and PDA testing. I have over 40 years experience working in all areas of the piling industry: construction, consulting, government and academia. Piling has actually been my passion since childhood. My father was a bridge construction contractor, and I was always particularly fascinated by the pile driving. My industry experience has led me to understand that current driven piling acceptance practice around the world does not provide quality assurance for the whole project. I needed to find a better way forward, and this led to the invention of the pile driving monitor. The critical design requirement for most driven piles is to achieve a compression capacity. Of course, the capacity needs to be verified. Normal practice is that we rely on evaluating the capacity of only a small percentage of the piles. There are two main options: static load testing, which is expensive and time-consuming, and if used at all, may be applied to 1% or less of the piles on the project. This is not statistically significant and can't be used for control of driven pile acceptance. Dynamic pile testing, which is also known as PDA, is combined with wave equation analysis and may be typically applied to 3% to 10% of piles on the project. By comparison with static load testing, this is a statistically significant percentage. Nevertheless, this still leaves 90 or even 99% of the piles on the project untested, while actually every pile is equally important. For these untested piles, we typically reach back to those methods used before PDA testing was invented back in the 1980s. Before then, dynamic formulas were used for pile acceptance. Unfortunately, many studies have shown that dynamic formulas are very unreliable, and so these formulas had to be used with very large factors of safety. The PDM was invented to partner with PDA testing to extend the reliability of PDA testing to every pile on the project. Every pile on a project is equally important. Each column sits on one or more piles, and that column relies absolutely on those piles for its support. The piles under any particular column may be statically or dynamically tested, or in most cases, not tested at all. As much as is possible, we should try to provide each column with the same reliability of support, or at least the maximum level of reliability which is practical. Providing each column with the same reliability of support would actually imply either statically or dynamically testing every pile. This is clearly impractical, both in terms of cost and time. Because of this, we have no choice but to use simple methods of capacity evaluation, such as dynamic formulas. But what we must do is to ensure that these formulas are site calibrated and use accurate and verifiable inputs relevant to each individual pile. The new third generation PDM achieves this and much more. There are literally dozens of dynamic formulas that have been proposed and published over the past 100 years or more. What virtually all formulas have in common is that they are relationships which link energy, E, movement, M, and capacity, C. In all these formulas, capacity is inferred from the relationship between the energy input and the movement response. With very few exceptions, pile driving formulas are all EMC relationships, In fact, even bearing graphs are an EMC relationship. It is very common piling practice to assume that hammer efficiency is constant as measured by the PDA, and that the energy delivered is known and constant. On that basis, it is usual that all piles are driven to a fixed set value. This approach is actually an incorrect application of an EMC relationship because it assumes hammer efficiency to be constant. In reality, studies have shown that hammer efficiencies vary by 35% or more during the course of a project. So assuming a fixed set criterion is wrong. Actual delivered energy must also be taken into account, and this is a key benefit of PDM monitoring. It is very important that when applying a pile driving formula, not only the formula is calibrated against PDA test results, but that the formula uses the energy delivered to each individual pile. And of course, that the pile set and rebound are accurately, reliably, and safely measured as delivered by the PDM. The PDM uses two advanced methods to evaluate capacity. One is an improvement on a traditional energy-based formula, and the other is a new approach based on measurement of impact force. In order to improve dynamic formulas, it is necessary to first understand that dynamic formulas do not predict pile capacity. They predict pile driving resistance, which includes both static and dynamic components. To predict pile capacity, the dynamic component must be removed, which is exactly the same as for PDA testing. By correlating PDA with PDM, we define a dynamic reduction function, which is a variable correction factor based on pile set. For high sets, DRF is maximum. For low sets, it's minimum. This approach has been verified over many years and on thousands of pile installations. The other pile driving formula implemented by the PDM3 is a force-based method. The ratio of pile capacity to impact force is a variable function which is maximum at low pile sets and decreases as pile set increases. This function can be predicted in advance by wave equation analysis and then confirmed by PDA testing on site. Because the PDM not only measures pile set, but also measures pile velocity, the peak impact force and the pile capacity can be calculated. This alternative acceptance method does not require measurement of delivered energy. PDM3 measures set and rebound with an accuracy of 0.1 millimeters at a distance of 10 meters from the pile, and even more accurate at closer distances. Pile velocity can typically be measured at an accuracy of 0.1 meters per second, depending on the hammer type. This ability to measure pile velocity is a game changer for piling. The PDM3 is a rugged, non-contact, high-speed infrared camera, specifically designed for the construction environment. This new generation PDM is capable of simultaneously measuring the position of 10 targets 8,000 times per second and as many as 32 targets at lower frequencies. The PDM3 is designed to be a practical tool for use on every pile because, as I've emphasized, every pile on the project is equally important. Minimum pile preparation is required. No drilling, no tapping, no bolts, no wires, just peel the backing off the reflector and attach it to the pile. The PDM automatically computes the distance to the pile and adjusts for any pile rake. No need for measurement of distance or of pile rake. Setup is very fast. Place the PDM on a tripod, connect it to the tablet with a USB cable or Wi-Fi, aim the PDM at the reflective tape and start recording. There is no delay to piling. The PDM3 can be placed as close as 2 meters or as much as 50 meters or more from the pile. No engineering knowledge is required by the operator. All pile details can be entered for the project by engineers in advance of the project and just imported into the PDM with a thumb drive. Site personnel only need to enter the pile number, penetration, and start recording. It's a piece of cake. The PDM can be used in 2 modes, either for tracking object movement along a vertical or horizontal line, or to detect multiple objects moving across an area. Although capacity verification for driven piles has been the initial purpose for developing PDM3, its capabilities allow the PDM3 to be used for many different monitoring tasks in pilot projects. The measurement of pile velocity not only allows peak impact force to be evaluated for use in advanced pile driving formulas, but has additional benefits for driven piling. They are evaluation of pile length and evaluation of pile damage location and severity. By attracting reflectors along the pile length, the pile driving monitor can provide a full load count versus penetration report. PDM can also be used for vibratory pile installation monitoring, which is a preferred method of pile installation, particularly for some marine projects. The PDM3 can provide QC reports for the full pile installation, including vibration frequency, amplitude, penetration rate, and driving force versus penetration. PDM can also be used for jacked pile installation monitoring, which is preferred in some areas and has advantages for silent and vibration-free piling in urban areas. PDM3 can accurately measure the pile movements, including creep movements during application of the final holding load, which are important for jacked pile acceptance. A final load movement curve can also be included in the QC report. The PDM3 can be used for static load testing by remotely measuring movements of the pile head without the need for any reference beams. All types of load tests, compression, tension, and even lateral can be monitored. The PDM3 provides real-time tracking and professional load test reports. The PDM3 is truly a versatile measurement device for any type of preformed pile installation. Finding a stable reference during marine piling is always a significant challenge. The PDM3 can be used to measure both pile set and rebound from jack-up and floating barges, with full adjustment for wave effects and tidal movement effects. Future developments will enable the PDM3 to provide real-time set, rebound, and blow count records, even in high sea state conditions. The ability for PDM3 to measure from long distances provides the opportunity to place the PDM3 on previously driven piles, for both pile driving and static load test monitoring. Undertaking static load tests offshore without any need for reaction piles or reaction beams is game-changing. The PDM3 provides unprecedented capabilities to marine piling, and every marine piling project should use one. The ability for PDM3 to measure in both line and area scanning modes provides great opportunities to provide important monitoring functions in many aspects of construction and infrastructure. All the functions I'm about to describe are currently possible, but the following functions will be supported by specific applications under future development. Structural monitoring of static and dynamic loading on bridge structures. The PDM can also measure rail performance, the performance of the rail, the ballast, and the subgrade under static and dynamic train loading. The PDM can also be used for vibratory compaction monitoring, measuring compaction frequency, amplitude, force, and the amount of compaction for each pass of the compaction roller. Measurement of ground vibrations and structure vibrations for protection of buildings and infrastructure during piling projects. The PDM3 is a multi-function device that provides benefits over a wide range of civil engineering applications. Development of the PDA provided tremendous advancements to the evaluation of single piles in the 1980s, but extending the benefits of PDA to the whole project and the 90% or more untested piles has never been properly developed. The PDM provides this project-wide quality assurance benefit. The piling engineer can now properly verify the capacity of all piles to a high standard without imposing significant costs, because every single pile matters. The PDM3 combines the latest optical technology with decades of piling and civil engineering experience to provide contractors, consultants, and infrastructure owners with a powerful quality assurance system. I'm Julian Seidel, and this has been my PDM story.